Okay, at 20 degrees Celsius, an aluminum ring has an inner diameter of 5 centimeter. So you see, you have to change this as to SI unit. Okay, mark it down first. Need to change this into meter SI unit. And then you have a brass rod with diameter of 5.0500 centimeter. Again, this is non-SI unit. You have to change it to meter. Okay, given the coefficient of linear expansion alpha, yeah, he give for both material, aluminium and brass. We have two objects here. One is aluminium ring, another one is brass rod. Okay. If the ring is warmed, what temperature must it reach so that it will just slip over the rod? Okay. Only first situation is only the ring is warmed. What temperature? So we want to find temperature. Yeah? We want to find temperature. Where it reach so that it can just slip over the rod. Okay, let's look at B also. What if both the ring and the rod are warm together? So for B is another situation. Both ring and rod warm together. Okay, for question A is only the ring is warm. Yeah, we only heat up the ring. But for B is both the ring and the rod are heated up. Okay, both the ring and the rod are heated up. So for this situation, what temperature must they both reach so that the ring barely slips over the rod? So this one also find the temperature. Okay. All right. Okay, I draw you a picture already, like this one, right? Okay. So we have two objects here. We have the aluminum ring. Okay, if you see here, okay, just highlight. We have aluminum ring and also a brass rod. What we want to do is we want to let the aluminum ring. This is the aluminum ring. Okay. Yeah, this is the aluminum ring and this is the brass rod. We want the aluminum ring to slip over. Yeah. We want it to slip over. I mean to pass through the rod. We want the aluminum ring to pass through the rod, but it seems that the aluminum ring has a smaller inner diameter. The aluminum ring is only 5 centimeter. So I want to write that down over here. Yeah, so the inner diameter of aluminum ring is only 5 centimeter. Okay, however, the brass rod has a bigger diameter, 5.05 centimeter. So that's for brass rod. The brass rod. This is the brass rod. The diameter is 5.05. 5.05 centimeter. Okay. So how to pass the aluminum ring? How to pass it through? Yeah, how to pass it through? Because the aluminum ring is smaller, the brass rod is wider. So how to pass it through? So that's why question A, we have to heat up the ring. When we heat up the ring, yeah, we heat up the ring. This ring will expand. It will expand. Maybe I will draw. It will expand. Yeah, it expand. Then he can pass through. Okay, he can pass through. Okay, before that is small. So we want to find what temperature it expand. Yeah, we want to find what temperature it expand. Yeah, until it can pass through. Yeah, before that is very small. And at what temperature? Oops, excuse me. Okay. So when we heat up the aluminium, it will expand from 5 cm going up to become bigger and bigger. So what temperature it will slip over. That means this aluminum have to expand until bigger than 5.05 centimeter, then only can slip over. Okay, so we can say that okay, this is about the area. What we are going to do is we are considering about the area. The area, yeah, inside, yeah, the inner diameter area and this diameter of the rod. So what we have to do is we want to find the temperature when these two area become equal. Yeah, we have to expand, make it this is the case. Yeah, that means we want the aluminum ring to expand from heat it up. Yeah, we heat up the ring. Okay, we heat up the ring. Okay, heat up the ring. We heat up the ring so that it expand from 5 centimeter diameter to 5.05 centimeter. Then it can pass through the the rod. Okay, so what we have to do is we just find about the increase in the diameter. Okay, increase in the diameter. So we use the formula. Okay, length is the final length is equal to the initial length. Okay, 1 plus alpha delta t. Okay, 1 plus alpha delta t. The length we refer to diameter. Okay, refer to diameter. So this is the initial diameter, and then 1 plus alpha. Okay, we are considering this is for question A. This is for question A. So we are considering only the ring. Yeah, only the ring is heated up. Only the ring is heated up. Okay, so so this one alpha, we use the alpha for aluminium. Yeah, we only use the alpha for aluminium, and then this one use the final temperature minus the initial temperature. Okay. So okay. So we just substitute. The value inside. Remember this this part. This temperature here is about the or we can say this change of temperature. You can either use Kelvin or degree Celsius. You no need to change to SI unit because change in temperature, the increase of 1 degree Celsius is the same as the increase of 1 Kelvin. Yeah, we mentioned this before. Okay, but the rest you have to SI unit. Yeah, the rest you have to be SI unit, meter. Okay. All right. So what's the diameter for this one? Anyway, okay. Better you change the diameter into meter. Yeah. Or actually, we can also maintain as centimeter because these two has the same unit, isn't it? These two have the same unit, centimeter. So they can cancel out the unit. Yeah, that means they have same unit. Yeah, they won't affect much. Okay, so we can just put 5 centimeter and the 5.05 centimeter. Okay, so what we want to achieve here is initial diameter of the ring is 5 centimeter, and we want to initial diameter of this is the initial and this is the final. We want to heat up the aluminum ring from 5 centimeter to 5.05 centimeter before it can pass through the brass rod. Okay, we have to make the inner diameter of the aluminum ring to become the same as the diameter of the brass rod. Okay, so this is the final diameter and this is the initial diameter. So let's put inside this is the final diameter, 5.05 centimeter. This one is initial diameter is 5 centimeter. Yeah, never mind, you can put this centimeter because they can cancel. Yeah, and 1 plus aluminium, we're using aluminium 24 exponent -6. Yeah, exponent -6 multiplied by this final temperature minus initial temperature. initial temperature is 20 degrees Celsius. This one you don't need to change Kelvin because I mentioned just now you can maintain as degrees Celsius. Okay, so you can put as 20 degrees Celsius. So later your temperature you also get in degrees Celsius. Yeah. Okay. Okay. So now let's find out the temperature. Let's find out temperature. Okay. I've done the working here. Okay. Yeah, just divide 5.05 divide by 5. Okay. And then minus 1. Okay, and then divide by this value. Then finally I get the temperature in 436.67 degrees Celsius. This one in degrees Celsius because just now initial temperature also degrees Celsius. Okay, so the answer slightly different. Okay. Okay, we hold on for a while. Yeah, so maybe the answer different is because they round up the value during the calculations. Okay, so this answer should be correct. Okay, that's the temperature. Okay, anyway, this is we using the diameter. Yeah, we are using we look in terms of diameter. Okay, we looks in terms of diameter, so we use the linear. Yeah, so we use the linear or the length. We use the linear or length formula. Okay. However, we also can investigate the area. Understand? Investigate the area, and let's check. Do we get the same temperature? Do we get the same temperature if we use the area formula? Okay. Now let's find out using area. Okay, area. So for area, we use a formula area equal to area initial 1 plus. This one is beta. If area using beta. If linear length, we use alpha. If area, we use beta. Okay. Beta, delta, t. Okay. And then be mindful that beta is actually 2 alpha. Beta is actually 2 times alpha. Yeah. 2 times the coefficient of linear expansion. Okay. So right now we are using aluminium. We are just investigating about the aluminium. Okay, we only heat up the aluminium. The final area of aluminium, and this is the initial area of aluminium. Okay, 1 plus this is 2 alpha. This is for alpha for aluminium. Yeah, 2 alpha. Yeah, because beta changed to 2 alpha. And then final temperature minus initial temperature. Let's find out, can we use the area and do the temperature, we get the same answer? Okay, but how to find the area? Diameter for area for a circle is actually what's the formula for area for a circle? Area for a circle is actually pi r square, isn't it? Pi r square, or if we use diameter, it become if we use that, radius is actually diameter divided by 2. Diameter divided by 2, so it is actually pi d square over 4 after we expand, isn't it? Pi d square over 4. So let's find out. Okay, pi d square over 4. All right. So we get okay. So this one we use pi d square over 4. Okay, let's find out the value first. Okay, before we do anything. Yeah. So this one is pi. Okay, I just want to 1 second. Yeah, don't want my work to become messy. So this is what I do. Yeah. Okay, so this one we put as pi d square over 4. This is for the aluminium. Okay, and then initial area is pi d. We use initial diameter. Okay, pi d square over 4 also. This for aluminium also. And then here also 1 plus 2 alpha. Okay, put in the value of you know, the value of alpha. Alpha just now is 24 exponent negative 6. Okay, put in the value there. 24, excuse me, 24 exponent negative 6 and t minus 20. Okay. Hold on a second. Okay. And then, oops, sorry. Okay, t minus 20. Okay, so what we can do here is we can cut all the common. Okay, this is the common thing we can cut off. The 4 here also. And then what else? Okay, we can put in the value for diameter. The diameter is final diameter is 5.05. This one is excuse me, 5.05 centimeter square, and this one is 5. Initial you start with 5 centimeter. Okay, diameter, and then this 1 plus 2 alpha. 2 alpha become 48. Okay, exponent negative 6 bracket. This is t minus 20. Okay, let me work it out. Yeah, let me work it out. Okay, so I put in the values here. Okay, and this one I divide. Okay, and minus 1, and then I divide and I find the temperature. I got the temperature equal to 438.75 degrees Celsius. Oh, and this answer is 438.75. Let's check the answer. Yeah, the real answer is 438.75. See that? 438.75. This is correct, 438.75. Okay, I finally got the correct temperature. But how about the first method? Yeah, I have shown you two methods. This is the first method and this is the second method. So, is the first method correct? I use the diameter. I find the expansion of diameter from 5 cm to 5.05. Yeah, 5 cm to 5.05 cm, and I got the temperature. You know, I got the temperature 436.67. But if I use the area, okay, expansion in area, we use the pi d squared over 4, pi d squared over 4, expansion, I got a temperature 438.75. Different answer. So this one is about area. Okay, whether or not the ring can pass through the rod is about achieving the area. Yeah, achieving the same area. It is not the diameter. It's not the diameter. It is the area. So this method, you shouldn't use the diameter. Yeah, you shouldn't use the length. This is wrong. Okay. Many students made the same mistake like what I did just now. Okay, they just use the diameter to find the temperature, and you get a different answer. Okay, definitely, because what's important is the area of the aluminium need to be the same area with the brass rod cross-sectional area. Yeah, the area of inside the inner area of the aluminium need to be equal to the cross-sectional area of the brass rod before the aluminium ring can pass through. It's not the diameter only. Yeah, it's the area. Yeah, the area. So if you talking about area, you need to use area. Don't just use the diameter. Okay, don't just use the diameter. Okay, so you get a wrong answer. This one is correct. Okay, must use the area. Okay, so do not use the diameter. Do not use the diameter. Use the area. Yeah. Be careful. If you use diameter, you get a wrong answer. Okay, so use the second method. Don't use the first method. Now, okay. Next is what if what if both the ring and the rod are warm together? What temperature must they both reach so that the ring barely slips over the rod? Now the second situation is both of the ring and the brass rod, they are warm together. Both expand. Last time is just the ring expand. Now because last time question A, you just heat up the ring, so only the ring expand. Now you heat up the ring and the rod, both you heat up together, and both also expand. So if both expand, if ring expand, brass rod also expand, will they achieve the same area? Is it possible? Question C, would this latter process work? Explain. This one you have to refer to the alpha value, the coefficient, the ability to expand. So it seems that even though the aluminum ring is smaller, compared to the brass rod diameter, but the aluminum has a higher alpha value compared to the brass alpha value. So aluminum expand faster. We can say that aluminum has a higher alpha value, so aluminum, the ring will expand faster than the rod. So at certain temperature, they will achieve the same, they will achieve the same area. Okay, so for this one, how to do? Also, we must use the area. Don't use the diameter. Okay, so for question B, let's see how we do it. So for question B, we heat up both together. Question B, we heat up both together. Last time is just heat the ring. This question A is heat aluminum ring. Question A, heat aluminum ring only. Now question B is heat both ring and rod together, and both expand. You can say both expand. Okay, so both the ring and the rod expand. So for both to achieve the same area at certain temperature, in order for the ring to slip over, so for ring to slide over, so the final area, this is important, the final area of the aluminum of the ring need to be the same as the final area of the brass rod. This is the ring and this is the rod, isn't it? At a certain temperature that we want to find, this is our target. We want to find this temperature. Okay, so at what temperature? So we want to find the temperature when the final area, when we heat up both. The ring and the rod, so both will expand. Both expand. Okay, so at certain temperature, the final area of the ring and the final area of the brass rod will become equal. When they become equal, when the ring and the rod become equal area, then the ring can slide through. And we know that the aluminum, this is important, the alpha value of aluminum is bigger than alpha of brass, so aluminum expands faster than brass. So it is possible that the ring expands faster than the rod, so they will achieve the same area, the same area at certain temperature, even though initially the ring is smaller in area compared to the rod. But since the aluminum expands faster than the brass, so surely at certain temperature, this aluminum ring will become same area with the brass rod area, so then the ring can slide over the brass rod. Okay, so now let's find out, this is the most important, equations here. Okay, this concept. So we apply the same formula. Area, use area, don't use diameter. If you use diameter, because the diameter length is only reserved for what? length is only reserved for, let's say you want to find let's say a rod. You're given a rod. Okay, this is the initial length, and then you heat it up. The rod become longer. Not so long. Yeah, become longer a bit. Yeah, longer a bit like that. You see that? This is the delta L. This is the L, the whole length L naught. This is the L naught, and this is the L final. Okay. This is the L final. Okay. So this for length, for rod, yeah, like using a rod. Then we use this formula. Okay. Then we use this formula, the length formula. Okay. But talking about diameter, don't use the length. Yeah, don't use a linear formula. Talking about area, use the area. Don't use diameter to find. Yeah. Okay. Back to this question. Just now you say that because both ring and rod expand, so at certain temperature, for the aluminum ring to slide over the brass rod, they become same area, final area at certain temperature. So this is the temperature we want to find, and we use the area formula. This one, A naught 1 plus beta delta T. Yeah. Okay. And of course, beta is 2 alpha. Okay. 2 alpha. So okay, never mind. Let's do step by step. Let's do this step by step. Okay, this is a final area. Final area of aluminium is initial area of aluminium. Okay, and then 1 plus beta. Area use beta, yeah. Beta for aluminium, and then final temperature minus initial temperature, and then equal to. Okay, let me slide over. Slide over here, yeah. And then final area of brass rod is initial area of brass. Then 1 plus beta for brass, and then T minus T naught. Okay. So okay, so this one, area of circle is pi d squared over 4. Pi d squared over 4. So this is just put the bracket. I just put the whole bracket here is for aluminium. Yeah, I'm lazy to write so many symbols. And then 1 plus beta. This is also beta for aluminium. No, alpha already. Yeah, beta is 2 alpha because you are given alpha value. And beta is 2 alpha, isn't it? Beta is 2 alpha. So substitute beta with 2 alpha. 2 alpha. Okay, this alpha for aluminium, and T minus T naught. Okay, bracket. Yeah. Okay, now. Yeah. This diameter for aluminium. Yeah, initial diameter for aluminium. Yeah, initial diameter for. Okay. Write it properly. This initial diameter for aluminium. And then we have the brass. Also initial diameter for brass. Pi d squared over 4. And then 1 plus beta is 2 alpha. Yeah, 2 alpha for brass. And then T minus T naught. Okay. So this common thing we can cut off. You see that? This common thing can cut off. The pi we can cut off. The 4 also we can cut off. So what we want to find is actually this temperature. This is what we want to find, the final temperature. This is what I mentioned about the at certain temperature. At this temperature, the final area of the ring will become equal to the final area of the rod. So this is the temperature we want to find when they both become same area. Okay, both final area become the same. Yeah. Okay, so we want to find the T here. Okay, so the initial diameter for the the aluminium, initial diameter of aluminium is 5 centimeter. Aluminium is 5 centimeter, but the rod is bigger diameter, is it? 5.05. Okay, you can put as centimeter because this both left and right hand side have the same unit, so you can maintain as centimeter and no need to put exponent -2. Become messy. Okay, so the ring is 5 centimeter. 5 centimeter. This is excuse me. Yeah, this is the aluminium is initially only 5 centimeter. So then 1 plus alpha. What is the value for alpha aluminium? Aluminium has higher alpha, expand faster, than the brass. 24 exponent -6, much bigger. That's why it can become equal area. See that? And then we want to find the T, final temperature. Initial temperature is 20 degrees Celsius. 20 degrees Celsius. I can put this one. Okay, never mind. So this is 20 degrees Celsius. Okay. Okay. And then equal to for the brass rod, initial diameter is 5.05. 5.05. And then 1 plus 2 alpha. Alpha for brass is 19 only. Smaller alpha expands slower. 19 exponent -6. 19 exponent -6, and then T minus 20. Yep. Okay, so we want to find the T here. Seems a bit complicated, but we have to work it out. So I work it out for you. Okay, so I got the temperature is 2195.94 degrees Celsius. So a bit lengthy. So all the mathematics. So is the answer correct? 2195.94. 2195. This is 2197 compared to mine. 2197. 2195, which is 2196. So it's almost there. So it's correct. Okay, 2197, 2196. It's correct. Okay. So always use area. Don't use diameter. For circle, for area to match, you must use area, not use diameter. Don't use the length. Use the area. Use the beta. Beta is 2 alpha. Okay, remember that. Remember this beta is 2 alpha. Twice the alpha. Multiply 2 over here. Okay, so that's correct. To achieve the same, so at this temperature, the ring can have the same area as the rod. Initial temperature is 20 degrees Celsius. 20 degrees Celsius. So if you heat up both material, you have to heat up until 2000 degrees Celsius. 2000 degrees Celsius. If you only heat up the ring, then it's only 400 degrees Celsius. Okay, only heat up the ring is only 400 degrees Celsius to become same area. But if you heat up both objects, ring and the rod, then you have to heat up until 2200. From 400 you have to heat up until 2200. So it's quite a lot. Because the brass also expand together. But the thing is, the aluminium expand faster than the brass because it has a higher coefficient of linear expansion or higher coefficient of area expansion. Okay, so the next thing is, would this later process work? Would this later, can it work? That means, can the ring slide over the rod? Can the ring slide over the rod after this temperature? Sure, yes. Sure, yes. Can slide over. Yeah, so the answer I already given here. This is question C. Yeah, sorry. The answer is a sure yes. Yes. You must write yes. The aluminium ring can slide over brass rod after and after, yeah, temperature, which is after the temperature, which is what 2195.94 2195.94 degree Celsius. It can slide over, yeah, but must after this temperature. Before this temperature cannot, yeah. After and at this temperature and after this temperature can slide over, yeah. Higher than this temperature can slide over. Lower than this temperature cannot slide over. Yeah, can slide over, yeah. Explain. So why after this temperature can slide over? Because we can say the alpha value of the aluminium is bigger than brass. You must write also the value of the alpha, 24 and 19, yeah. Aluminium is 24 exponent negative 6 per degree Celsius, yeah. But the brass is only 19 exponent negative 6 per degree Celsius. The aluminium ring, I can say aluminium ring expands faster. The important keyword is expand faster than the brass rod. Yeah, this is about material. This is about the material coefficient of linear expansion, because it has higher, because it has, you can say, because aluminium has higher coefficient of linear or area expansion. Yeah, then brass. Yeah, if linear is alpha, if area is beta lah. Yeah, if area is beta. So these are the explanation you can give. Okay, higher coefficient of linear expansion. So okay, so that's all for these questions. Okay, remember, talking about area, don't use the diameter. Yeah, don't ever use the diameter. Use the area. Yeah, you must find out the area, pi d squared over 4, and beta is 2 alpha. Okay, and when you heat up both material together, then you have to consider both objects, both material. At certain temperature, they will achieve same area in order for the ring to slide through the rod. Okay, that's all for this question. Bye.